Hey, hi. Chapter 7. We're back. Some of your feedback said to have a little bit more excitement in my voice. And so here it is. 21 minutes of screen time last week. Thanks, iPad. Okay. So we're moving into Chapter 7. Similar or using some things from Chapter 6, but it is kind of a hard left turn. We're going to be learning about exponential equations and functions. In the first try, we really focused on linear and quadratic, so straight lines and parabolas. And in this chapter, we're going to be talking about something that are called exponential equations. So our EQ for this first day is how can I model exponential growth and decay using a graph or function? So as a quick warm-up, just to kind of get used to plugging this into the calculator, because this is what these things are going to look like. I'm going to type in 5 times 3 to the x power, but I'm going to use an x value of 2. So that means I'm going to type in 5 times 3 to the second power. Couple different ways you can type this in the calculator. 5 times 3 squared. You could just use parentheses instead of the times button. It really doesn't matter a whole lot. If that 3 was a fraction, then you would need to use parentheses. But we'll get into that as we move along. So this first one, 3 squared. You could also just evaluate this on your own. PEMDAS says to do this first. So 3 to the second power is 9, and 5 times 9 gives me 45. And that's where 45 comes from. Okay. So the next couple here are 4 times 2.5 to the x, but now our x value is negative 2. So this is 4 times 2.5 to the negative second power. Again, if we just type it in exactly as it looks, we know from last chapter that a negative exponent is going to move things into a denominator, which means we're probably going to have a fraction here. And sure enough, we have 0.64 as our evaluated value, 0.64. And finally, we have negative 1.5 times 0.5 to the x, where x is positive 4. So negative 1.5 times 0.5 to the negative 4th power to the negative 4. And that gives me, actually not a decimal, it gives me negative 24. And we'll talk a little bit about why that negative power came out to be a whole number, negative 24. Okay, so again, anytime you see the word evaluate, that means you're given a number and you're asked to plug it into a calculator and simplify it. Okay, so what we just plugged into the calculator are what are called exponential functions. And an exponential function is defined as anything that has the independent variable as the exponent. Okay, so the key difference is, like in chapter 4, we talked about y equals x squared. And even though this has an exponent, that exponent is fixed as 2. So that's not exponential. In order to be exponential, it needs to be the variable is what is in the exponent. Now, you might say, well, these are all variables. It's a, b, and x. But these two values are what we're going to replace with numbers. Okay. The a value is normally or sometimes called the starting value. You'll see other names for it, but we're going to refer to a as the start value of the function. So where are we starting out at? And then b is what's called the growth factor. Oh boy. Growth factor or the decay factor. And that whether it's the growth factor or the decay factor is going to depend on what the number is itself. We'll get into that a little bit, but this is how you're going to see it set up. It's going to be a number times another number raised to the power of x. Okay? So start value times growth or decay factor. to the x power. And that's what we call an exponential function. Easy. Moving on. So what does a graph of this exponential function look like? We plugged in some numbers. Again, like in order to get an idea of what the graph is going to look like, I'm going to go to the table. I don't want to plug in each of those numbers individually. So I'm going to go to the calculator and type in y equals 1.5 times 2 to the x. 1.5 times 2 to the power of x. And then I'm going to go to the table. Again, the table's right above the graph button. So if I hit second graph, it gives me this table of values. Now I know that I would like to have negative 2 to 2 is usually what we work with. You'll see here that negative 2 is 0.375, which isn't going to be easy to, not going to be super easy to graph, but we're just going to do the best that we can. So it was 0.375, 0.375, 0.75, 1.5, 3, and 6. Okay, and just to kind of, I mean, we'll allude to this in a little bit. The 1.5, it will show up in your table. Okay, you will see 1.5 in there somewhere. And then if you look at the pattern, what's happening as I go from value to value, that's where that growth or decay factor comes in. Since I'm multiplying by 2, the numbers are getting larger. So technically 2 would be called a growth factor. But just kind of a heads up, that's where those numbers are coming from. Let's see what this graph looks like. So negative 2 and 0.375, I'm going to do the best I can, right about there. And then it went to 0.75, then it went to 1.5, then it went to 3, then it doubled up to 6. I got those wrong. Those should be right there. Yeah. Okay. And so if we connect these points, so you can see it's kind of curving and growing. One interesting thing, if you look back at the calculator real quick, if I were to keep going backwards, negative 3, negative 4, negative 5, you see these numbers are getting smaller and smaller until it turns into scientific notation because there's such a small value. But you could keep hitting up and up and up forever, and the y value will never be negative. Okay, so it's a very, very small value, but it's not negative. So in the graph, when we connect these things, okay, we want to, nope, not that. We want to connect these points. Okay, I know the graph's going to keep growing, but you should not be crossing the x-axis. Okay, so that graph is going to come down and kind of flatten out, and it's never going to cross that x-axis, just because if I keep dividing if I keep dividing something by 2, it will never reach 0. And we'll kind of formalize some of that discussion momentarily. Another thing that you will see is you might say, well, if I compare these two equations, one of them is missing a number. And that is true. This 0.5 is the B value, or that growth or decay factor. If one of the numbers is missing, it's going to be the start value. And if it's missing, that's because it's 1. So if you wanted to put 1 times in there, just to kind of give yourself, keep it consistent, looking the same. So I'm going to go to the y equals. You can put the 1 in there. I'm going to show that we get the same thing. So I'm not going to enter the 1 in here. I'm just going to type in 0.5 to the x power and then go to the table. Again, I'm not worried about negative 12 for an x value. I want just from negative 2 to 2 to get an idea of what this graph looks like. So from negative 2, I have 4, and then I go to 2, to 1, to 0.5, to 0.25, and so on. So I come here. This was that was 4, 2, 1, 0.5, 0.25. And then we saw that the numbers will keep going and keep getting smaller and smaller and smaller. Okay. So again, I'm going to graph those. Okay. Notice again that our start value is in our table. and our 0.5 is what I would have to multiply by. So 0.5 multiplied by 0.5, so on, whatever. Okay. So -2, 4, and then -1, 2, 1, and then we got to 0.5 and 0.25. Again, now this one is coming down as I move from left to right. Again, the same rule applies. That graph's actually never going to cross the x-axis. It'll get close to 0, but it's not going to ever quite get there. Okay, so you'll notice that one of these is increasing, right? The first graph that we had started at small values and then doubled, and then the graph on the right starts high and is decreasing. That's the difference between exponential growth. Okay, so this is exponential growth because the graph is growing from left to right, or the y values are growing. Okay, and this is what we call exponential decay. So there's a visual difference between the two. Okay. So kind of a couple things just in general about an exponential function if it's written as a times b to the x. We saw that the start value is actually on the graph, and that start value is what happens if you plug in 0 every time. So picture this real quick. If I were to replace x with 0, 2 to the 0 power is 1. So then if I had 1.5 times 1, that would just give me 1.5 back. So an x value of 0 is always going to give you a y value equal to the start value. Okay. So one thing that'll always be true about these graphs, no matter what, is that it'll always start 0, a. And we call this the y-intercept. Where does that graph cross the y-axis? Okay. And if you think about what numbers we were multiplying by here, okay, so in this first function, I started at 1.5 and I was multiplying by 2. And since I'm multiplying by 2, that was making the numbers larger, which gave me exponential growth. Over here, I was multiplying by 0.5, which made the number smaller and gave me this exponential decay. That teeter line, the number that dictates whether it's growth or decay, is 1. So your growth factor, okay, when we talk about this, that b value or that number in the parentheses, the b value cannot equal 1. Okay, and the reason it can't equal 1 is because if you multiply by 1 over and over and over again, the values will never change, and so you just end up with a horizontal line. So if b is greater than 0, if b is greater than 1, yes, I hear you. If b is greater than 1, then this is going to give me exponential growth. And if the b value is between 0 and 1, then that's going to give me decay. All right, so also b has to be greater than 0. I can't have a negative growth value. Like, it doesn't really make sense for a growth value or a decay value to be negative. So if the number is bigger than 1, it'll be exponential growth. If the number is less than 1, it'll be exponential decay. Here's Puppy Dog. Somebody wanted to see Puppy Dog? Come here. Oh my gosh. This is Asher. Hi, Asher. This is the little one. The big one's down here too. Show you her real quick. There's Magnolia. Hi, Megs. Say hi. She wants to go outside. We got math to do. Yep. You smell things? Okay. Good talk. Gotta go. Ugh. All right. Anyway. So, growth and decay. And then the other interesting thing is that both of these graphs never cross the x-axis, and that will be true in lots of exponential exponential functions is that it never crosses the x-axis. Okay, so those are some generalizations about these functions. Again, we'll kind of formalize some of these definitions as we go along. Okay, so the completely new vocabulary that we're going to talk a lot about this chapter and also in chapter 8 is what's called an asymptote. There's a P in there, and you don't really say it. It's pronounced asymptote. Also kind of sounds like you're cussing, but you're not. Simply stated, an asymptote is a line that a function gets really, really close to, but never actually crosses or touches. And so both of these graphs, I made these graphs on Desmos. If you were to zoom in and zoom in and zoom in, like there's always a little bit of separation between the exponential function and that x-axis. And that's the same for whether it's growth or decay. So these graphs have what we call horizontal asymptotes. So what we're going to do when we're graphing these things is we're going to just put abbreviated HA at x equals 0. Or sorry, at y equals 0. Y equals 0. Because the y value is approaching 0 but never reaches it. Same sort of thing here. You don't have to say anything different. Even though it's decay, we would just say a horizontal asymptote at y equals 0. Okay, so that's that phenomenon where it gets really close but doesn't quite get there. So 4 types of exponential graphs. Just a little graphic organizer real quick. The first one is positive growth. And you might say, why positive? But we'll look at it. So positive growth means that you are starting at a positive number. And since it's growth, that means the b value is greater than 1. Okay. So a graph of positive growth is going to look something like this. Where again, and I'm just going to put this on there, that coordinate is always going to be 0, a. And I'm going to label that for all 4 of these. Okay, so positive growth, a is greater than 0, so you're starting at a positive number and you're growing, you're multiplying by something bigger than 1. The other one that we've already seen is negative growth, or sorry, that's a precursor of things to come. The other graph that we just saw on the previous slide is positive decay. So you are starting at a positive number, but you are decaying, so that means that the decay factor is between 0 and 1, so 0 point something. That's where the graph is going to start high and then come down and approach 0. Again, never quite getting there. And just for effect, again, crossing at 0, whatever a is. So those are the 2 that we've seen so far, but there are also the negative versions of these same things. Okay, there is something that called negative growth. And that's where we start at a negative number, but our growth factor is greater than 1. So that means our numbers are getting more and more negative. So I'm starting at a negative value, so this is really poorly done on this end of it. It starts flat and then kind of grows away from 0. Again, stressing this is 0, a. So you should always know one coordinate on one of these functions, even without typing it in the calculator. Finally, the last one's negative growth. That negative growth. Nope, we just did that. Negative decay. Caught myself. So negative decay means we're starting at a negative number and our growth factor, or in this case, our decay factor, is between 0 and 1. That graph is going to look something like this. And you might say, well, that's growing because it's going up, but it is in the negative sense, right? The number's decaying because it's getting closer to 0. Okay. So those are the 4 types. If you see something to the x power, it is going to look like one of these 4. There's no tricking. There's no fooling. Like there's that. It will be one of those 4 things. Okay. So just to test this real quick, and just obviously you have to do this on your own. Actually, now I'm realizing it's not going to be covered up. That's fine. So let's just look at some of these exponential functions and decide whether or not they are growth or decay. It's just a big long list of them. Okay. The 1.2 times 1.84 to the t, my growth factor is bigger than 1, and I'm starting at a positive number. So this is going to be positive growth. Okay. 3.26 is a growth factor, and starting at 8,000, this would again be positive growth. 0.1 times 5.092. Again, to find growth or decay, look for the number underneath the exponent. Look for the base. That base is 5.092. So again, we have a positive growth function. Realizing now that all these are positives, I should probably throw some negatives in there. Starting at positive 7.3 and then 0.64. So there's our first example of decay. Because our decay factor is 0.64, when I multiply by 0.64, the value is going to get smaller and smaller. Here I have a decay factor of 0.95, so that is again positive decay. I shouldn't really need negative numbers. Here we're starting at 1,212,000, and our decay factor is 0.004, so that is positive decay. That number is gigantic, but it will decay very rapidly. Okay, so look at the second number. Look at the b value to decide if it's going to be growth or decay. All right, now this is why we do exponential growth, and that's why this chapter is so useful. Is because a lot of things, especially when you're talking money and credit cards and loans, are expressed as percent change. But they follow an exponential growth or decay model. So the two formulas look very similar. The only difference is if I'm growing, I'm going to add, and if I'm decaying, I'm going to subtract. Okay. The rest of it's the same. A of t is what I'm just going to call it the future value of something. So how much is something worth? How much will something cost in a certain amount of time? Okay, this is why we want to be able to answer these questions about how much something will cost in the future. We have the small a value, this lowercase a. That's the same as earlier. That's our start value. That's how much we're starting at. Our r value is inside the parentheses. That is the rate change. So what percent rate are you, is something changing at? Is something growing by 3%? Is it decaying by 7%? The key to this is that the percentage needs to be expressed as a decimal. And we'll see what this looks like in just a minute. And then finally we have t, which is time. So however long you're talking, if it's years, if it's months, if it's days, t is time. Generally, especially if you take like a managing your money course, this is generally years, but there are exceptions to that. So, future value, start value, what's your percentage rate change, and then what is the time. So look at an example here. The number of drivers under the age of 20 in Minnesota has gone down each year since 2001. Again, public transit, trains, more access to getting around, especially in the metro area. Not every student needs to be able to drive. So in 2010, there were 280,000 drivers under the age of 20, and that number has been falling 2% every year. How many drivers are there in Minnesota under 20 years old today? So it's a word problem. There's going to be lots of word problems. That first sentence it gives us context, but there's nothing about this that we're going to need. Okay, that's just a lot of times just giving you background information. In 2010, there were 280,000 drivers. So that is going to be important somehow. With that number falling 2% every year. And I underline both the 2% and the falling because that means we're going to have a decaying function. We're going to be losing drivers, or the number of drivers is going to be going down every year. How many drivers are there in Minnesota under 20 years old today? So today, again, is the year 2019. So if we kind of identify some of these things, I don't know the future value, right? That's what I'm trying to find. So you can use this A of T. You're not going to always see A of T for the future value. You can see F or whatever. Our start value is what we need next. Even though we're not starting in the year 2010, that's our first data number that we're given. So we're going to say 280,000 is our start value. Then we always have to put 1 in here because, again, that's kind of the teetering point between growth and decay. So if I just kept it 1 and I multiplied by 1, we'd have 280,000 drivers every year for the rest of eternity. That's not happening. We're actually falling by 2%. But again, this is the key part. 2%, do not do this. Okay, don't just put 1 minus 2 because that means you're multiplying by -1. If I were to take 1 take away 2, that'd be -1, and our growth factor cannot be negative. This happens a lot. We need to change this 2% to a decimal. Okay, so 2% as a decimal. If you want to, however you remember how to change a percentage to a decimal, you can divide it by 100. You can move the decimal point 2 spots to the left. However you do it, this is 0.02, not 0.2, because that is 20%. Okay. So when we talk about this, if something is falling 2% per year, we're going to put minus 0.02, and then I need the time. Our base value of 280,000 was in 2010, so we're talking 9 years later, so I'm going to raise that to the 9th power. Okay. The only thing I'm going to clean up in here is that decay factor. 1 minus 0.02 is 0.98. And if you think about what that means, if I'm losing 2% of drivers every year, right, the number of drivers is going down 2%, that means I'm keeping 98%, right? Because 2% are the number is going down 2%, so we are retaining 98% every year. The nice part about this is I'm just going to type that in the calculator exactly as that looks. So 280,000 times 0.98, 280,000 times 0.98 to the 9th power. That means today there are approximately 233,449 drivers. 233,449. 233,449. Nope. 233,449 drivers today. Again, these are drivers that are under 20. So that's how we can use that percentage rate of increase or decrease to find us the amount of something down the road. So we're going to look at one more example real quick. If you want to try it on your own, go for it. Mr. Luke can invest $5,000 in an account paying 4.2% interest annually. So every year I get 4.2% interest, which means the account is growing by that much every year. How much will his investment be worth when he retires in 30 years? So again, our start value is going to be that 5,000. I need to start by multiplying by 1. A of T. We're finding the future value. In investments, it's called an annuity, is why we use the letter A. Just throwing that out there. 5,000 times 1. Hopefully my account is growing, so I'm going to do 1 plus 4.2, if I move the decimal point to the left 2 spots, would be 0.042. So that's what I'm going to put in here. And then I want to know how much will it be worth in 30 years. So my growth factor is 1.042. And then I'm going to raise that again to the 30th power and type it just like that. So 5,000 times 1.042 raised to the 30th. So after 30 years of gaining interest, that $5,000 has turned into $17,179 and 15 cents. $17,179 and 15 cents. So the money more than tripled in 30 years, and granted that's a long period of time, but 4.2% is a reasonable amount of interest to accrue. And that's why they say you want to start saving for retirement as early as you can, because the longer you keep that money in there, the bigger it gets. Yeah, I know. The video's done. We're going to go outside. Okay? Are you good? There you go. Homework 7.1, 3 to 42 every third. See you later. Do.